Hello, Gondo. Can you hear me? I think he can't hear me. Let me check something. Okay, so confirm that Gondo can't hear me. You should be able to hear me now. All right. Hello, everybody. Let's see who's here on chat. Looped Helio, Zombie, Sleep Poke, Cherney Charo, Sleep Repeat, Oscar. Hey, how are you? Super Normal Like, Evil. And look at that. We Gitalos just subscribed to the Twitch Prime. Thank you so much, man. Yeah, and also Gondo is here in chat. Who's this guy? All right, so Gondo needed elaborate to teach some PCB. Even though I think I'm a lost cause, I don't think I will be able to learn it. But he insisted, so we're gonna be, trying to do this Shark 50 PCB. Do we have the layout? I think you sent me the layout. Let's see. Sure. Oh yeah. Sure, we will do that. Let me just open up the thing you sent me. Hold on, let me download it again because it was at a different computer. There we go. So let's see here. Okay, hold on. Let me fix that. Oh my God, we try to make everything perfect, but it's almost never possible. Hold on. Let me see routing. Okay. Let's see chat mic. I can hear you fine. No, it's hold on. I think I know what it is. Let me see something. Chat. Try saying something now, Gondo. Can you guys hear him now?
I'm a Stegosaurus. Can you guys hear me?
There we go. All right. Sorry for the technical issues. Alexa, awesome. Turn streaming lights on.
Despacito.
Good. All right. So we're going to share the stuff that we did on GitHub afterwards. Awesome. I think that's part of what you've been saying and people couldn't listen. I am now uploading the layout that you sent me. So this is what we're going to do, right? Are we doing, and we're doing, not this kind of split space, right?
Well, that's on you.
Let's do 270. Let's do the usual
stuff. If I can remember correctly, we did set on another layout. That's a 40% that I was discussing with T today. Let me check.
Isn't this the one, Gondo?
I don't think so, no. Let me see.
Isn't it the 50% that you sent me last?
I think it was a 50%, yeah. It was for a case that Shark was designing, if I can remember correctly.
I think this is the one, then. The one that I have on my screen right now.
Let me see. Well, we can do it anyways. Let's do it.
Why? This wasn't the one?
I don't think so. That was one that I sent you today, right? That I asked you an opinion on.
But isn't this one the... Hold on. This isn't the Shark 50, so it isn't this one.
No, it's not. That one is a 40% one that I was discussing with T today, and I sent you and I asked you for like an opinion on the layout.
Oh, okay. So
the one we did set on for the stream was one that Shark was developing, I guess.
I thought this was the one. So hold on, guys. Sorry for the...
So we Gitalus says he's going to bed right now. So yeah, nighty night, man. You can...
Yeah, have a good night.
After Keebs releases the VOD.
So let me see here. Okay, do you have a key KLE available, Shark? If you want to send me, I can use that.
He did send me a Kelly.
For me as well. Let me see. If you have it, send it again.
Da-da, elongate shenanigans, pills.
I think this is the one. Hold on. Got it. This one.
Why do we talk so much? Goddammit.
There we go.
Let's see. Let's see.
Can you double check on those?
Yes, that's the one.
Cool, cool. All right. All right. Okay, perfect. So this is the layout we're going for. All right. Yeah. So should we start? Where should we start, Gondo?
First of all, by the way, my camera does not look good. I'm checking on stream right now. Yeah, awesome. First of all, we should start with KiCad, right? So first of all, install KiCad.
I do have it already. It's already
You have
open.
it installed.
And I have a Shark 50 project with a blank PCB and a blank schematics.
Let's see that. Okay, so first of all, we start by the schematic, right? So first of all, but before trifling with schematic, we need to download the necessary libraries.
Right.
These libraries will include symbols and the footprints for the switches. Although I think the latest version of KiCad, it had a native Emacs switches support. So
Native what?
Check the KiCad people incorporated Emacs switches footprints onto KiCad.
Okay.
Yes, they did. They did, yeah. So I don't think we will need any more libraries.
Okay.
No, we'll not. Awesome. So first of all, we should start with the microprocessor, right? Because every project that we do with a PCB, it will basically be the same, almost the same microprocessor-wise.
Mm-hmm.
Well, first of all, we set up the microprocessor.
So open up the schematic.
Open up the schematic. Yep.
Done.
Awesome. Now you add the microprocessor.
How do I do that?
Awesome. You add a component.
Where is that? Place?
Exactly. Place. And well, first of all, let's start with like the basics, which is the AVR, right? ARM is basically the same. For a beginner, what will change are the pinouts and stuff. So you place symbol.
Okay.
Awesome. And you click anywhere on the schematic.
Should I put it down here? Or does it matter?
You can move it afterwards. So okay. For now, anywhere will do.
Okay. What are we looking for now?
So a window should pop up and you should type in ATmega.
Oh, hold on. There is something I can do. I can share my screen with you. Oh, but then people will see my screen and not your face. Hold on. Let's try that because I think it will make your life easier. Hold on.
Yeah, if you could share your screen with me on Zoom, that would be better because I'm checking your screen on your screen on stream right now and it has that little delay.
Yeah, let's do that. Hold on. Let me try.
If you could do that, that would really help us.
Okay, I need to mute myself. Now we should... hold on. Yeah, now... Yeah, there is an issue. Hold on. Let's see.
Maybe you could share your screen with me on Discord. That would be kind of easier.
Yeah, let's try that. Hold on.
Try that.
Let me see. How do I share again?
You make a call,
Okay.
join, and then there is this little button there that says turn on screen share.
Yep, got it. Oh, and Discord
You
just
left.
crashed. Yes, hold on.
What the actual heck?
I'm gonna try it again. There we go.
Do that.
Turn on screen share. Share. Can you see my screen? Okay.
I see you. Awesome. That's awesome. Yeah.
Perfect. All right.
Okay, so now, now that the little window has popped up for you, you search for the microcontroller name, which is ATmega. The default microcontroller for QMK is the ATmega 32U4. So I'm going to check the big name.
Yeah, this one I'm used to. Do you wanna grab this from keyboard parts?
You actually don't need to. I think the MCU library, which is a native one on KiCad, has that already.
Yeah, but it's a different footprint. Can you see my screen? Like the one on keyboard parts.
It's actually a different symbol, right? Not footprint. You
Yes,
can use
correct.
both. You can use any one you choose.
This one seems more organized, doesn't it?
Okay, fair enough.
No, but from your perspective, I'm learning.
The problem with that is that the keyboard and align parts library is one you downloaded, right? It's not.
Yes.
It's not present stock like on.
Oh,
on
so let's. Can we take that out?
So it's preferences, manage symbol libraries, and there
keyboard
should
parts.
be.
Yeah, let's remove this.
Parts.
I want to make this. How do I?
The last one, you. Yep.
All right. So place symbol is Shift A. Let's place it here.
You're using Mac, right? Maybe the shortcuts on the Mac are a little different, but on Linux and Windows it's just A.
Here is Shift A.
Okay.
So this is the footprint, right? AU, MU.
ATmega 32U4. Yeah. The differences between them, the AU and the MU are the package types.
Yes.
Right?
Okay.
So what is that basically? And that would be like this. Can you share my screen in a stream right now?
Yeah, hold on. Yeah, you need to share it on
Zoom, right?
On Zoom, yes.
Okay, let me do that.
By the way, I want to cap this first episode to 1 hour.
An hour?
Yeah, so let's go to like 6:30 our time.
Okay, awesome. So I believe you're seeing my screen right now?
I am.
Yes, you are.
Oh, so Demon is with Amit right now. They're both together. That's so cool.
Are they? That's awesome. So if you go to the LCSC site and you type in ATmega 32U4, you will see 3 types, right? Which are AU, MU, and MUR. The MUR, if I remember correctly, is a deprecated one. You shouldn't use that. Instead, you should use the other 2 ones. What's the difference between them? It's the package.
Right.
So
AU is the smaller one, right?
The one is generally used is the QFN, I think. QFP, sorry.
QFP.
And the MU is the QFN package. If you take a close look, the QFN package doesn't have the exposed leads. So you need a hot air station to solder that. You can hand solder that one.
I'm showing, I think, AU on my screen. Hold on. As soon as focus works, I will try
Let
here.
me see that.
This is AU.
No, that's not. That's
MU. MU, I'm sorry. Yes, and AU is the one we use on keyboards normally,
right? Is that the Elite C?
Yeah, this is an Elite C.
Okay, so yeah, that's the MU. To use that, you would need the hot air station. You can't solder that by hand.
True.
So Regalicia says, using the keyboard part library probably isn't a huge deal with the demographic you're designing it for.
Oh, yeah, so the thing is that now per Gondos. We now have MX switches on the main one, right?
Yeah, it would be easier if you could just use it out of the box, but the user can, use any library he or she wants. That's
Right.
not a big deal.
Right.
But we want to keep things simple, right? So everything out of the box.
Correct. All right.
So,
oh, sorry.
okay.
I was not sharing your screen anymore.
No, I was just showing the different 18 mega packages.
Right.
So this is the AU, right, which is the one that we are used to, that has the exposed LEDs. And this is the MU, which is the one you just shown them.
Perfect.
The MU, it's significantly smaller, right? So it has its uses when space is a concern, but that's just not generally a problem with keyboards. You have plenty of space in PCB, right? So now that we have the microcontroller, we have to power it on, right?
Yeah.
So first of all, we are going to tie the pins 2, 14, and 24, which are UVCC, VCC, and AVCC. Those three ones, they look different, but they are fundamentally different, right? AVCC is the pin that powers the analog to digital converters, and the digital to analog ones, it stands for analog VCC, right? And UVCC is the if I remember correctly, is the reference voltage for the USB.
Okay.
But externally, they are just the same. You're going to connect them to like 5 volts.
Okay.
So if you try to place a component, there is like a symbol for 5 volts. There is an actual symbol for 5 volts.
Got it. Do you want me to show you mine, or do you want to use?
Yeah, I can't see your screen on Zoom anymore, on Discord anymore. I can't see why.
Oh, hold on.
Let me see.
You should. Hold on.
Okay, I see you.
You see?
I see you.
Okay.
And you just wire those guys to 5 volts. You wire by using W.
W. Can you see what I'm doing?
I have no idea why your screen on Discord is frozen. It's completely frozen.
Hold on. Let me see.
Absurd. Don't sweat it though.
Stop sharing. Let me try it again.
On stream.
Let me. Yeah. Hold on. Frame rate. Start. No, right? Can you see? I think you can.
Yeah, I do, but for some reason it freezes. But anyways. Okay, they are wired. And well, you will need also to wire the ground, right? Which is the pins on the bottom of the symbol.
Okay, and then do I add a ground as well?
Yeah, there is a symbol for GND, which stands for ground. Let me put the camera here.
GND.
GND, that's the one.
And then why is the component name here on the... Can I change the location of this?
Yeah, you can perfectly change the location of that, but it would be like cleaner if you could move the labels. So the U label, you press M and you move it.
Ah, nice.
See?
So do I put it down here?
Well, you could put it like inside the symbol. That would look better. Yeah, like somewhere you could see it.
Cool.
Awesome.
So now I can move the ground like here. Is that?
Yep.
Okay. Oh, and by the way, in Mac you don't need the shifts. It's just the same, just W and just A.
It's just the same.
Yeah.
Awesome.
So I'm gonna wire those two, right? Like this.
You wire those two. Awesome. So if I remember correctly, the AVR, you also have to use a capacitor on the UCAP pin.
Sorry, D-Law just followed. Thank you for the follow, D-Law.
Oh, awesome, man. Thank you.
All right, sorry, you were saying something.
Okay, so there is a pin on the 18 mega, which is UCAP, which is pin 6. It's on the left side of the symbol. There you go, UCAP. See there on the top of your screen?
UCAP, yes.
So you are going to add a capacitor symbol.
Okay, let's go. So A and then cap.
Yeah, I like the C underline small symbol, which is a little bit smaller symbol for a capacitor, which looks
Nice.
better in my opinion, right?
Perfect. And then should we put it right here on the...
Okay, so you have to put it between the UCAP pin and ground, right?
Okay. So here, for instance. Oh, so you put another ground.
Yeah,
Okay.
like you wire UCAP to that capacitor and the other end to GND.
Got it. Let's do that. Hold on, I'm just moving those labels aside. And now let me... Oh, you can rotate it, right? How do you rotate?
You can with R.
There we go. Better. Okay, let me move this back. Okay, let me do this. Can you undo? Yes.
Control Z, if I remember, right?
Yeah, that's correct. Okay, so let me move it back. Oops, upwards here, and now let me rotate. Yeah, that's better. Okay, let me rotate this, and let me rotate this. You can clearly see that I don't know what I'm doing, but I'm trying. And now let's move this one down here. Okay, and now let's wire. Let me just move this to be perfectly aligned. And now let's wire this. Oops. Move to here. And now let's add another ground here. And now let's wire the ground. Oops. Wire the ground to the capacitor. Is that how it's supposed to look?
That's exactly how it's supposed to look. But for, you also should set the value of the capacitor, right? Which should be a microfarad, if I remember correctly.
1 microfarad?
1 micro. So you could do just 1 U, right? You know that's a microfarad.
Right. Like this?
Yeah, your screen went black for me. But yeah, exactly like that. The C, like question mark, would be like a C1, a designator, right? C1, C2. When you leave the question mark, KiCad will like number it automatically for you.
Ah, really?
So, yeah, you could just leave the question mark there and it will annotate automatically for you.
That's something I didn't know. Nice.
Yeah, you can just leave it.
Okay.
Awesome. That UCAP, it's remember UVCC, right?
Yes.
It works as a capacitor for holding the reference voltage of UVCC. That's why it's needed. If you guys have any more questions and if you guys want to take a better look at why this is, you could see the datasheet, the microprocessor datasheet, and there is an awesome application note by the very manufacturer. I am going to put the link for
I'm showing it.
Chat. Yes, that's the data sheet. On the data sheet, let me open the data sheet here too. So summary data sheet. So 27 pages. Let me see. If you search there, UCAP. Okay, there you go.
Yeah, I see it.
It says...
I'm almost there. I passed it. Hold on.
You passed
it?
Here.
Okay,
so...
Here, right?
Yeah, on my data sheet here that I got, I don't think which one you are using. It says something like this. Let me send you the link so you can get it. Okay, I sent you the link on Discord. It says on page 6 that UCAP is the USB pad's internal regulator and that it should be connected to an external capacitor of a microfarad.
Right. There's also the block diagram. It shows UCAP. I'll show you that, but let me find.
Yeah, I see it. I see it.
Should be connected to external capacitor of 1 microfarad.
In microfarad, exactly.
Cool. Nice. That's very... Yeah, I never understood where those values would come out of.
Yeah, that's basically capacitors. These particular capacitors, they are used for bypass, which is holding a voltage, which electronic people call bypass, and the power people call a voltage regulation.
Okay.
When you have noises on your 5 volts, the capacitor is responsible for holding that voltage to safe levels and filtering the noise, right?
Right.
That's why this particular capacitor is used.
Very nice.
Okay, so now we should see VBus.
VBus,
is a pen that monitors voltage. It monitors the USB voltage, and it should be connected directly to the USB voltage. In this case, 5 volts, right?
Okay. So do I add another 5 volts?
You add another 5 volts. Why is this important? Because some people will use the 3.3 volts. For the microprocessor for various reasons. Sometimes it is good to use 3.3. If you use 3.3, that pen should be connected to the 5 volts. Anywho.
Okay.
Okay, so I see you're connecting it. You can just connect it without a wire, to be honest.
Oh, I see. Hold
see?
on. Mm-hmm. Done. No, it's not connected. Hold on.
Yeah, that's it. That's connected.
Okay.
There you go. So now what we should do is what? Yeah. The pin AREF is a reference voltage for some regulators, and it should be just left alone. You shouldn't connect it, right? Pins 16 and 17 are for the crystal, right? For the oscillator crystal. So let's add an oscillator crystal. So if you add a component, if you just type in crystal, you will see a bunch of components.
Hello,
right?
Tefram. Yes, I see a bunch of them.
And for now, let's use a simple oscillator, which is a 2-pin crystal, right? Particularly, then again, I like to use the crystal underlying small symbol, which is a little bit smaller and makes for a better, cleaner schematic.
Perfect. Got it. So do I put it between the 2 Extel pins?
Yeah, you should put it between the 2 Extel pins.
Let me rotate. Okay, and now is there a particular order? Should I
it's not. No, there's not. You can rotate it any way you can. We will now need to put the load capacitors, right?
Okay. Right. There's a capacitor that goes in between the crystal and the crystal pins, right?
No, it's between the crystal. The crystal is directly connected to the pins on the MCU.
Okay, so I can wire them.
You can just wire them, no problems.
Okay. All right. And now the capacitors?
And now the capacitors should be between the crystal pins and ground.
All right. Do I add another ground, or do you usually reuse one of the grounds we have?
Just keep adding the ground. The same symbol, if you use the same symbol, it will refer to the same net. So you can just add another one. You can just copy the past one also. You don't need to keep inputting, placing. You can just press C and you copy the GND
Perfect.
symbol.
So I just pressed C. And now, let me see something. I used to have an application that showed the keys that I pressed, but it's okay. We don't need it now. All right, so where should the ground go now? Oh,
Okay,
you're
so
already adding a capacitor. Let me do that.
yeah, you have to add the caps.
It's just cap, right? The one you what?
C underline small.
Oh, and
You can
hold
copy
on.
for the one that's already there too.
I just lost everything. KiCad
What the
crashed.
KiCad crashed?
Yes, it closed,
But
and
that
I have.
almost never happens.
Are you being sarcastic?
Yes, I am. It happens a lot. It shouldn't, but it does happen a lot.
Okay, and I think I didn't save anything, so let's double check. But I think I can re-add everything quicker if we need to. Is there an auto save or something like
I
that?
can send you the schematic file too on Discord.
Oh,
And you
there's
can
a
just
saved
paste it.
schematic here. Let me see what that
Is
is.
there?
Yeah, and it's from 4 minutes ago. Let's see.
Let's see.
If not, you can send me. Oh, it didn't open with saved schematics here. Let me see.
Yo, so there's Tefrem. Hi, Tefrem. How are you? Late to the party again. Don't sweat it, my man. We are here. I wonder what causes KiCad to be so unstable. Just, normal bugs. KiCad is a very forgiving program once you learn to use it. And the first rule of KiCad is keep saving. Anytime you make a modification, you press the Control S and it just does the saving.
Okay, so we lost the V bus. So if you want to send me yours,
Okay, will do.
zip it and put it on.
I'll send you just the schematic file.
Yeah.
You just copy it.
I will.
Where's Shark? Okay, so I sent it over disk.
Okay, let me copy it over. Replace. Let me delete this saved stuff. Let me open the Pro. Now I will save it.
I think it won't work because the file I gave you has like the lowercase first s. You should rename it to the high case, tall case first s.
Let's do it. Oh, but it did work.
Did it? Ah, awesome.
Here we are. Okay. Back to normal.
Awesome.
So let me just recap what you did. First, what I did before was wiring this to this 8 megahertz that you didn't tell me. What is 8 megahertz in this context? Is that the oscillator?
That's the oscillator frequency.
Why is that the one that I used was 16 megahertz?
You can use 16, you can use 8. That's really not a big deal. Preferably use 16. I goofed there. You can use 16 or 8. That's not a problem. For like the available speeds and frequencies, you can always take a look at the datasheet, right?
Yeah, now I will because it's awesome. And I never knew this.
Okay, so in the datasheet it says 8 megahertz at 2.7 volts and 16 at 5 volts, right? So if you're using 5 volts, which we are right now, use 16 megahertz.
Oh, okay. Got it. So, yeah. So, and then you added two 22 picofarads capacitors.
Yes.
Is that on the data sheet as well?
No, it's not. Those 22 picofarads, they are kind of standard for this value of frequency, right? But you can use them, no problem. Like the board will work, but for optimized working and to know that it's for sure under specifications, you should take a look at the crystal data sheet. Right?
Okay.
So you are going to, when we are going to order the components and see which component is available, which is like on the middle stages of the development, you have to select the crystal there and see the datasheet, and it will tell you which value you should use. But 22 is generally the value, right?
Got it.
So
okay.
22 is a pretty good first use.
Perfect. All right, we can move on.
Okay. Awesome. Okay, so this is the basic first setup, right? For the 18 mega, there you have also to use a resistor for this particular pin, which is pin 33, right? So if you take a look at pin 33, it says HWB, and this is basically
hat.
the boot selector.
Okay.
So we have to add for that pin a 10K resistor.
Okay. Let's see. Resistor. How do you add a resistor?
Then again, I like particularly, that's my thing.
R
I like
small?
to use the R underline small. Yeah.
Okay. Perfect.
That's actually my ringtone.
Yeah, I figured. All right, I have the R small. What is the value? Right? 10K?
10K, and you add it from the pin 33 and ground.
Okay, mine doesn't align as perfect as yours, though.
It should, though. Why doesn't it?
I don't know.
Oh, it's because of the grid. So you go up there on view. Where's your menu? There should be like a menu.
Units? No, not units. Yeah, I'm on view here.
View, and let's see. That should be like something like grid settings.
No, I think it's on here. It's on preferences, maybe. Preferences. Icon options, hotkey, set language, tools. I don't know. Maybe it's the version that is different because it's not.
Maybe, yeah. See if you have another like a menu that you can search for the grid settings.
I'm trying to. Hold on.
I have here file, edit, view, and place.
Let me see. Grid.
That's strange, though.
Show grid. There is show grid and then there's units, but there is no. Maybe this. No, this is to show the grid.
That is strange.
File, import, export, page settings. Let me see under preferences. Hold on.
See.
Grid size here.
Grid size, use 25. It's 50, use 25.
Got it. All right. Let's see if
and now it should align.
It does.
Just
perfect.
Good. Awesome.
Oh, so you need a wire there, or can I connect?
You can connect it. You can just connect it. I like to wire, but okay. You can do your thing.
No, let's do the Gondo style.
Opa Gondo style.
Opa Gondo style. And then let's copy like Gondo told me to do. So I'm copying the ground here. And then let's move it here. And then wire it like so. Perfect.
Awesome. And now we are set. The only thing that we would add now is check if your V-bus is connected to 5 volts, because mine is not.
Which one?
Your V-bus, pin 7.
Okay.
Is it connected to 5 volts?
No. Let's do it.
Do it. Do it.
Do it.
You know that Palpatine meme. Do it.
What is that?
The Imperial the Palpatine, Senator Palpatine. What's his name? He's like the Emperor in Star Wars, the bad, evil Emperor.
Oh, I don't know.
There's this meme. He says, "Do it."
Sorry.
Okay, so we are almost done. The only thing that we should add now is that little net for the reset, right? Which is the reset button. The hard reset button.
Here, pin 13.
How this works is through a, we call it a discharge net, right? A discharge net. And how that works is basically that it's like this. You see that reset button there? It's negated, right? It's not reset.
Oh, I think I learned about this. Is this the active low, active high kind of thing?
Exactly. Okay. Exactly. This is
active low.
An active low. So you want this to be 5 volts in normal usage, and in the reset usage, you want it to be
ground.
0. You want it to be pulled down. So the way we do this is through a very clever circuit, which is like this.
Let me show your screen. I can show your screen.
Can you see my screen? Okay. 1K here, and then you add a cap here. This cap, I think 100 nano will do. And then you add a, are you seeing? Yeah. And then you add the switch button. The switch button is SW, I think it's, let's see, push button. Yeah, it's SW underline push.
Okay, I'm not doing anything. I'm just watching, and I'm gonna do that afterwards.
Yeah, so it's like this, right? And you add it like somewhere like this. The this resistor here, you will use something from 1K to 10K. 10K maybe is better in this situation. And how this goes is like this. So let me show you. Here, 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 and then you add the GND.
I didn't know that you could do that. One wire for the whole thing.
That's the hex. Let me just move the labels a bit to make it clearer. Oops. Here. So what this is see this middle pin here.
Mm-hmm.
So in normal usage, the capacitor is an open circuit. It's charged. It doesn't conduct any current. It's an open circuit. So this pin here, it doesn't conduct any current. So this middle guy here is 5 volts. When you press the switch, it shortcuts that pin to ground. And therefore, the middle pin becomes GND. See?
Okay, so not sure I understand. So, hold on. So if the switch is not closed, it is connected to what? To ground?
Yeah, in normal operation, the switch is an open circuit, right?
Right.
So it's like it doesn't exist. It's transparent. So it's something like this.
Right.
Also in normal operation, this capacitor here is charged. So it doesn't conduct any current. So it's also an open circuit. So it's like, it would be like this.
Okay.
So this guy here, he doesn't conduct any current. Current doesn't have anywhere to go. So the voltage difference here is 0. So this middle pin here is also 5 volts.
Okay.
This is normal operation, which is what we want to, right? We
Right.
want the reset to be 5 volts because it's inactive. Now,
Right.
when we press the switch, what happens is this. So the cap discharges,
Mm-hmm.
and this pin here becomes 0 volts. And that's how you tell the MCU to reset.
And where do you connect the pin?
To like this.
Okay, I still don't fully understand. Hold on, let me see if I can understand it. So, why? So, as you said, in normal use, it's going to be 5 volts, right?
Yeah, let me add like a label here so we know which pin we are talking about. This guy here.
Mm-hmm. Right. I still don't understand why it is 5 volts.
Okay, so in normal use, when you didn't press the switch yet, right? So the switch is an open circuit, so it's like it doesn't exist, right? It's like this.
Right.
Also, in normal use, in permanent, in a static behavior, we say, the capacitor is charged. It doesn't
Okay.
conduct any current, so it's like this, right?
Right.
It's just an open circuit. So this RST here,
It's 5 volts, I understand.
see, it's 5 volts. This is normal usage.
Why do you need the thing that I don't understand is why do you need the resistor there?
The resistor is, because if the resistor is not there, when we press the switch,
It's still going to be 5 volts?
no, it's
No.
not. You make a short circuit, a plain, we call it a hard short circuit between 5 and GND. You're going to have a very high current here. See? You are shorting 5 volts and GND.
Okay.
So what's going to happen is this connection, which is this wire here, it has a finite resistance, albeit small, but finite.
Mm-hmm.
So you are putting 5 volts through a very, very, very small resistance. So the current that this wire here conducts is very, very high. It's very high.
Right.
So you add the resistor there so that he limits the current, right? See? Now the current that goes through this pin here is 5 volts divided by 10K, which is half a milliamp.
I'm going to pretend I understand, but I don't.
No? Okay,
No.
so let's try this. The wire here, this wire here is a copper wire in the PCB, right? It's like a copper trace.
But before you do that, let me ask you something.
What's that?
Why isn't, because let's pretend that we don't even have the switch. We just have the reset button connected to a resistor that is connected to 5 volts, right? Let's forget about the rest of the circuit for this explanation.
Sure.
Why?
It's like this.
Yes. Imagine it's just that. Isn't that preventing 5 volts from going into the reset pin? Isn't that like the same amperage that you say, like 50 milliamps or whatever you said that time?
RST is what we call a tri-state pin. It's a very, very high impedance. It's a very, very high resistance. Imagine it's like a mega ohm resistance.
Okay.
So it's like circuit-wise, it's like it was also transparent. It's like this. It doesn't conduct any current. See, so you can kind of pretend it doesn't exist. Kind of.
No, but in normal operation, the reset pin must be 5 volts, right?
Sure.
The part that I don't understand is how is 5 volt reaching the reset pin if we have that resistor in between?
Awesome. So since this guy here, the reset button, doesn't conduct current, it's a very, very high resistance. Can you agree with me that the current through this resistor here is very, very small to the point that we can consider it like null?
Yes.
So if the resistor doesn't conduct any current, the voltage drop in the resistor is very small. It's like, if you take a look at the equation, it's voltage equals resistance times current.
Okay.
If the current is very small, is 0, the voltage is also 0. So this voltage difference here between the resistor pins is 0. So this guy here is 5 volts.
I think the problem is that I don't fully understand the concepts between resistance, voltage, and current. But that's okay. Let's move on. I can try to understand that later. Okay. So let me do that. Let me add the same. So what happens is when this is closed, or when the switch is pressed, the reset pin is gonna short to ground, right?
Yeah.
And when it's in normal operation, it's gonna be connected to 5 volts.
Exactly.
Okay. So let me try
What I like to do, most people generally don't like this. What I like to do is also adding a resistor here. Right before the switch. Let me add this guy here.
How do you delete something? Let me show you my screen.
It's either delete or backspace. Both work.
Okay. All right. So let me add the switch.
It's SW underline. It's SW underline push, if I remember correctly.
Yes, it is. Okay. And then I need a resistor. Oops, I pressed R to add a resistor. How stupid am I? Hold on. Then
okay, so Tefrem is asking, what is the purpose of the crystal? The crystal
can I try to answer that?
Oh, what's that?
And then you can
No problem.
You can correct me if I'm wrong. So the way I understand it is that the crystal is there to ensure that you don't have like a steady flow of current throughout the whole thing, right? Instead of having like a steady line, what you're doing is you're having a frequency, right? So you can think of as sickles, imagine a heart pulsating some blood into your veins, right? Every time there is a pulse, is a cycle, and then the processor is not gonna be constantly processing something, if you will. It's gonna do that every so often, right? So every time the crystal generates a pulse, it's one cycle of operations that the microprocessor is gonna do, right? It's, you can think like of you have games like Civilization where it's like a turn-based game. So every time, like every cycle, you need to move your stuff and then wait for the computer to change their stuff, and you can only do something again on the next cycle, right? So that's what the crystal is for, to make sure that we have, you know, cycles to interpret the things that it needs to do. Basically, you can like fix what I said. Gondo.
Yeah, that's exactly what it is. So this is something like this. The microprocessor is basically a fast calculator. That's what it is. It does calculations fast. What the crystal is he is a clock generator. So he generates the pulses which tell the processor that he can calculate. So imagine a square wave, right? That's what basically the clock is. It's a square wave. When the square wave is on the high part, is when the microprocessor does one calculation. So each square is one calculation, and then he turns down. And then in the next cycle is another calculation, and then he turns down. And that's cycling, you know, and that's the cyclically, if we may, doing calculations. That's basically what the crystal does. It generates that clock. That timed signal that tells the microprocessor to do calculations is what we call clock. We use crystals basically because they are the most accurate way of generating that clock. So nothing is perfect in nature, right? So that resistor that we are adding of 10K, he is not going to physically have 10 kilo ohms, right? He will have something between, I think normal resistors have a 5% tolerance. So he will have something between 9.95 and 10.05 K resistance. I'm sorry, 9.5 and 10.5. The crystal is the same thing. Yeah, he's not going to have 16 megahertz, like exactly 16.00000. No. He will have something in between a spectrum of values, but he is very accurate. That's why you use quartz crystals. It's a quartz crystal, basically.
So I'm almost there. I created I just forgot the 5 volts.
Awesome. You add the 5 volts there. So Demon says, Gondo, put your phone on silence mode. Yeah, I did. And I told my dad's calling me. It was my dad calling me before that. I told him that I'm busy.
Okay, so now what am I missing? I need to connect this to the reset?
You have to connect the bottom part to GND, right? The other
Oh,
pin,
right. Yeah.
Remember that?
Sorry, I completely forgot about that one. So down here at the bottom, you have GND. Maybe I can move it so that it connects from here, like this. Okay, perfect.
Awesome. So what we need to do is see that middle between the capacitor and the resistor, right? Mm-hmm. You would wire that to the reset pin. Try doing that. You will have to do a very
long,
nice, very long. So what we do here is we use labels. We use labels. Particularly for me, I like what we call global labels.
Okay.
Which are these kind of red arrows,
mm-hmm.
right? And we add global labels by doing exactly what you did, right? There is also a hotkey, which was, I think it was K, I don't remember.
Mine is Command Shift H, I think.
On your right side, you can see the red arrow there,
mm-hmm.
and you have like place global label.
Yes.
And then and then you connect it to the net that you are placing like the label. You connect it to that middle. Yeah, exactly. Now that middle, we call it a branch or an S. That middle guy there, he's called it's called RST for reset, right?
Right.
To make it like look like an output, because you can see that the direction of the arrow is like going in.
Yes.
You have to edit it. You press E to edit it.
E?
E.
Output. Okay, so hold
And
on
then
because I...
put output.
Okay, hold on. Let me press E and then output. That's awesome. Got it.
See? And then when you want to connect it to the reset pin, you add just another label and then you name it also RST.
Mm-hmm. Let me... So it's... Wow, the shortcut is crazy. Oh, and it didn't even work. Hold on. Place, global label, RST, and then this one is input, right?
This one use input.
Cool.
Awesome. Okay, so when if you need to check if stuff is connected, you use what we call net highlight. So
Okay.
if you take a look at your right, at the top, you will see like a pink
Yes.
zigzag.
Uh-huh.
It should be called highlight net.
Yes.
Then you click that guy and you click the RST name there.
Okay. It seems like it didn't do anything. Hold on, let me try it again. Then, yeah, I click it, but nothing happens when I click it.
But nothing happens.
No. I don't know what the problem is.
Try in the middle between the resistor and the capacitor there.
Yes. Now it did.
So everything that's pink right now is connected.
Nice. Nice.
So this is a good way to check in your schematic and to highlight what is connected to what, right?
And it's the small things like learning is so nice. This is super useful.
It is, right? It is. So if, for example, you name one of the labels wrong, like I'm going to name one of them wrong. I'm going to name one RST and the one I'm going to name reset.
Right.
Right?
Let me do
when
that.
you highlight it again, the other one just fades. Yeah, just try doing that.
Yep. Doesn't work anymore.
So now you can see that they are not connected, and then you're going to say, yeah, they should be, and then you're going to see what is wrong with them.
Love it. Love it. So let's see here. Now it's connected again. How do I... Well, there we go. Perfect. Let me save because I didn't save. Now it's saved.
Yeah,
okay.
You have to keep saving, otherwise something's going to happen.
All right. So we have the little reset circuit.
Okay, so for the people seeing on stream, this is your basic, how would I say this? The basic setup. This is the bare minimum that you should have in order for your microcontroller to work, right? So you have everything. You have the reset, you have the crystal, you have everything wired. So this is how every project starts. We're going to build it up from here.
Mm-hmm.
Right?
Yes, perfect.
Awesome. Now I'm going to go into a very, how can I say this? It's not controversial, but it is highly technical, which are the bypass capacitors.
Okay.
If you take a look, do you have the Elite C on hand with you?
Mm-hmm.
Okay. If you take a look at the Elite C, you will see right, that near the microcontroller there are very small capacitors right near it or
Here?
right under it. You see, right near there are three small capacitors. Those are called bypass capacitors, and what they do is basically filter noise.
Yeah, right? There is one to one side and two on the other side. I see it.
Yeah. Why are there three? Well, conspicuously, you have three 5-volt pins, right? You have UVCC, VCC, and ADCC.
Yes.
So you have to add a bypass capacitor for each one of them.
Okay.
right? Their values should be in the data sheet. Let me see if I
Bypass,
find.
pass, low pass filter, AVCC, capacitor.
On the complete data sheet, there should be something like this. Bypass. Let me see. This kind of thing is a problem because the exact value you have to generally search like in the complete data sheet. And let me see if I can search the bypass
VCC, USB, crystal, VCC, ground.
I am very used to the STM32. I have been working, but the 18 mega is, I have to search for it still. Let me see, resetting, power supply, power management, I think. Yeah. There's some clocks, extended. No, this is not. For it was something like yeah, I found it. So it is
Where did you find it?
For
can you send me the link? I can open it here.
Yeah, I send you to this. There you go. I sent you.
Okay, here.
So, design considerations, it says AVR 042.
So this is the schematics for the Teensy, right? That uses the 80 mega, and it basically what we use for some keyboards if they have more pins than the Pro Micro, for instance, right?
Yeah, there is generally when you need to design hardware, the chip manufacturers will have what we call application notes, which are basically guidelines for you to use when you are designing hardware with their stuff, right?
Mm-hmm.
And the AVR has one, and I just found it.
Okay, send it over. Send the link.
And
I can open it.
I'm searching for the exact values. Here, I sent you. I can't find the values though. It says that there should be capacitors, but it doesn't say the high values. I remember them by hand. I just want to show you where they are in the data sheet.
Right.
But oh well, let me send you. So this is the application note.
Yeah, but I see on the first link you send me, it says it's 10 microfarads.
Yeah, for the 10 microfarads, you should use it for right after the connector. You should use a 10. But those guys near the microcontroller, there should be one
microfarad
for AVR, for the AVCC, and 100 nano for the two other guys. If I remember correctly, those were the values.
Yes, let's see if I can.
Right.
Yeah, it should be one for correct operation. Yeah, and can you can clearly see it here. Can you see my screen? There is a 1 microfarad here and a 1 microfarad here between the USB and UVCC and also V-bus.
See that the VCC and the UVCC, they have a 1 microfarad there, right?
Yes, here.
But for VCC, which on the which is pin 1434, and AVCC, he has 3 capacitors down there, which are 0.1 micro, which is 100 nano, right?
Right.
These guys, they should be placed as near of the pins as possible, of those pins as possible. Generally, what happens with them is we add them like this. So let me show you here, here, and here.
Let me show your screen to everybody.
Yeah.
I feel like the newer ARM chipsets are a bit easier to work with.
The new ones, they are, because actually the ARM is an industry standard, so you have lots of literature about them. They are very well understood. While AVR also are very used, they are not as much as in standard as the ARM are. So you have to dig a little bit deeper on data sheets and whatnot to find those kinds of things. Also, ST, the manufacturer of the ARMs, they have like amazing technical stuff. Their technical documents is very well written, easy to understand. It's awesome. It's really awesome. Okay, so we have a 10 microfarads guy, which should be placed right near the USB part. We have a 1 microfarad guy, which should be placed near AVCC, if I remember correctly.
So
I'm sorry, UVCC. This one should be placed near UVCC.
So it's a 10 micro. Then what's the next one?
10 micro. You have a 1 micro.
1 micro.
And 2 100 nano.
Okay. Let's see. Is this correct? What I have on the screen right now?
Your screen is kind of blurry to me. So 10, 1, and 200 nano. Yep, that's it.
Okay.
And they all should be wired from 5 volts to GND.
Okay. Okay, let me put it on the screen and you can double check if I did the right thing.
Awesome. Yep.
Okay.
That's right. That's perfect. That's perfect.
And why did you say this is very controversial?
This is very controversial because the problem with those capacitors, and we will see that when we place them on the PCB, is that they have to be placed in a very specific way for them to effectively work.
Got it.
Their usage is very well understood, which is, well, the noise problem, like filtering noises in power spikes and voltage spikes and whatnot. But their placement on the PCB is kind of controversial.
Okay.
So we will see how that should be, what's the right way to place and how to trace them.
Perfect.
So yeah, now we have a very basic, this is a very basic, how can I say this, template of how it should work. And this is a very basic first project. Everything comes from here.
Okay.
So just so we are clear, this is the bare minimum.
Right.
This without any of these guys, it won't work. Maybe without the reset net, but then you won't be able to reset your microprocessor. The only way you could reset it is by turning it on and off, which in the case of the keyboard would be keep disconnecting the connector.
Remember, we don't have USB.
Connector.
Shouldn't we add an USB now?
We will now.
Cool.
Okay, so does chat have any? Yeah, so OTRDL. What value are they looking for? I feel like they are okay. Microchip certainly nice, but the documentation is spotty at best. Exactly. That's what I said. ST, which is the manufacturer of ARM, has amazing technical documentation. Microchip has good stuff also, but it's not as good. So you have to keep reading the data sheets and searching for those values and checking if everything's correct. As you guys can imagine, this process is very it's very, how can I say this? You have to keep looking at the data sheets and looking at your schematic at the same time to see everything is the same as the data sheet specificates.
And I don't know what I did. I messed up with chat on the stream. I don't know what I did.
Chat is enjoying the masterclass. Yeah, man.
No, this is really good stuff.
That's why we're here. Okay, so now is everything good? I see your screen is looking good.
Let's just see if I can bring chat over.
Oh, you can bring the chat over to your screen, right? Something happened to the screen chat.
Yeah, I don't know what I did, but it stopped working completely.
That is not good.
Hold on, let me see something here. Let's see.
Just live stream things. Yeah. Oh, Top Clack is watching us. What the God? Thank you so much, guys. Just
who is this? Is it Jay or is it
or Quakems?
Or is it Quakems?
You probably reloaded it. Yeah, it's working, man. It was reset. Just
oh,
now.
Nice. Okay. And it's there twice now. Hold on.
And they subscribed.
No way. Thank you so much.
That's awesome, man. Thank you.
Thank you so much.
Quakems. Oh, thank you so much, man.
Really appreciate that, Quakems.
Thank you so much. Okay, awesome. So it should be working now. So this is the bare minimum we have, and now we should pass on to placing the connector. So the connector that we use is the simple one, the most simple one, and in my perspective, is the best one that new people should like the first newcomers that are designing PCBs should use, which is the Mini B, right?
Okay.
So I think that if you search in the components, you should use USB _B _mini.
Okay, hold on. Let me just put your face back here. All right, so let's see. USB underscore
USB _B _mini.
Oh, mini is the easiest one. Okay, let me grab some water. Hold on. So yeah, it's there on my screen. I don't know if you can see it.
Yeah, there you go. So basically, which pins are which? So VBus is the power pin, the 5 volts power pin. GND is your voltage reference, so it's like your 0 volts, right? We will leave shield away for now, but shield is like the outer that outer mesh on the cable, right? Which is used for protecting the signal inside that's passing through the cable. we will leave that unconnected for now.
Okay.
In any circumstance, connect that to GND. It's not a good idea to connect that to GND. Otherwise, your PCB will receive noises and the pollution, the noise pollution that comes from the shield. If you take a careful look, the shield is a mesh around the. You guys know what I'm talking about, right?
Yes.
Around the cable, there is a
the shell, yeah.
And that's basically an antenna, right? It's a long cable. So it's an antenna. So if you connect it, you are inserting noises onto your GND.
Quick question.
What the shield is used for is to manage voltage spikes, and that is implemented on the Akron PCBs, but you can leave them unconnected for now.
Okay.
The PCB will work. So for now, let's just leave it alone. You were going to ask something?
Yes. What is the difference between shield and ground? Because every time I have like how you call it, the thing that checks for continuity, the the thing that checks for continuity.
The multimeter. It's the multimeter,
right?
Yeah,
the multimeter. When I have that and I check continuity between shield and ground, it's always a short. Why is that?
This shield, it should be connected to ground through a capacitor and a resistor, a net in general.
Oh, okay.
Between the two points, like the two extremes of the cable. So in both sides of the cable, it should be connected to GND through a special net.
Got it.
Which is not that special, but it has its use, and that's why you see a short there.
Got it.
It's not actually like hard short circuited, but leave it alone for now. Like
for sure. No, let's do it. Let's continue.
So the D plus, and D minus are the data plus and data minus, which the microcontroller uses to like communicate with your computer, right?
Right.
The ID pin, we will leave it unconnected. The ID pin is a feature of USB 2.0, which allows the computer and the keyboard to know which one is the master and which one is the slave.
Got it.
That's used for like most serial connections has have a master and a slave, but we won't need that now. We can just not connect it. So we will need just 4 basic pins we'll use. The V bus, which is the 5 volts, D plus, D minus, and the GND. That's what we will do for now.
Okay.
For now, what we do is we connect V bus to 5 volts. So then again, we get our 5 volts and connect V bus. So my brain is too small and too smooth for this stream. Don't worry, man. We're trying to make it as easy as possible. Don't sweat it. If you have any questions at all, just ask us on chat, and we'll be really glad to help.
Oh, trust me, my brain is just as small when it comes to this kind of stuff. So I'm trying to finally learn how to design a PCB.
Awesome. And now we connect the GND, the pin 5 of the connector to GND, right?
Yes. Hey, .com, how are you? Yeah, I'm just trying to learn how to build a PCB, and Gondo is having all the patience in the world and trying to educate me.
That's not, man. I like you. I love you.
I love you too, man.
That's no
big
patient
hug.
at all. Now, the D plus and D minus. So if you take a look at the microprocessor, there are also D plus and D minus pins. You should not hardwire them.
Okay.
You should use, first of all, 22 ohm resistors between both of them. So it should look something like this.
This bromance is beautiful.
Oh, yeah, man.
This is the bromance stream.
The bromance. The bromance stream. Awesome. Yeah, bromance.
So I saw that you already copied from somewhere else to resist.
Yeah, I just copied it.
So let me do the same. So one here, and then one down here. And we can kind of rotate it. Oh, it doesn't work. Okay. Just move this. Oh, what is that? Let me see what you're doing because I completely. Hold on.
I'm just adding like these two
Okay. No,
resistors here.
yeah. Okay, fine. Hold on. Let me see. So let me move this.
So Super Norm Alike asks, will the stream be available later on YouTube?
Yeah, for sure.
Bring back this a lot. Yeah, sure, man. I forgot to tell that there are like wonderful resources on the community. There is that guy, I think it was Rui Kimal, the name of the guy. There is this like very good step-by-step guide on PCB design. Particularly, I really like AIO3's.
Oh yeah, AIO3 is the guy.
AIO3. AIO3's, he has also a guide which is wonderful. So that guide he has and this stream should make you really comfortable with designing your first PCB. Also, Top Flex says PCB designers are the heroes of this community.
Oh yeah, like we can't live without them. Doesn't matter to have. Doesn't matter if you have that beautiful keyboard if there's no PCB inside, right?
No PCB, right? You could hardwire stuff, anyways.
Yeah.
So yeah, we are disposable at best, man. Come on.
Nah.
So the two resistors that you have right now, they are 10K. They should be 22 ohm.
This is also known as 22R, right? Sometimes.
22R. Yeah. So for the
hey, look at that! Thank you, Top Clack. Yeah, don't forget it's September. So if you wanna sub, this is the month to sub. Thank you for the plug there, Top Clack. Yeah, it's half off.
That's awesome.
So go ahead, Gondo. I'm sorry. You were talking about 22R.
In the many times when you see like a schematic or something, you will see something like 1K5. Like, so 1K5 is a short way of saying 1.5K.
Right.
1.5.
I've seen that before.
Thousand. For resistors, the ohm, the single ohm is the omega, is the capital letter omega, if I'm not mistaken. So it's like it's the God of War symbol.
Right.
Simplify. It's the God of War symbol, right? And it's really difficult to type and to write the God of War symbol. So we instead use R. So 22R is 22 ohms. 22K would be 22,000 ohms. 1R5 is 1.5 single ohms.
Right.
5 is 1.5K. So that there are these little like notation caveats that we use generally. You could just use 22. If you leave just 22 there, most people will also understand.
Right.
So right.
Perfect.
And now you can connect them just the way you did. You already connect them. That's awesome. Let me do this too here on mine.
I can show you your screen real quick so people can follow. So now we're connecting the resistors in between the data pins from the USB to the data pins on the microcontroller.
So now our microcontroller should be able to be powered up and communicate with the computer. What is left now is to do the matrix, the switch matrix, and design like the layout of the keyboard.
It is the first time that I understand everything that is, around the microcontroller. I've seen that a ton of times, but I never understood what they were. Now, thanks to you, Gondo, I understand everything that we did. Cool.
That's no problem, man. That's really no problem. Not a problem at all. Okay, so just a small explanation. This can vary mildly in the sense that if you use a Type-C connector, the Type-C connector has to have a little bit more of components. It has to have like there are two pins on the Type-C connector, which are the CC, the CC1 and CC2.
Okay.
And those two should have like registers that tell the computer that you can export 3 amps of current. So for the Type-C, there is a little bit of more that you need to use.
Right.
Also in my PCBs, if the people in chat want to see the files of Acron, I will also add a little bit more things to this. So what is the problem here?
By the way,
Say for some reason that, oh yeah, awesome. If you take a look at my repos, but I think it would be better, Keeps, if you showed them the documentation, which
sure.
is gondolindrim.github.io. Let me put the link on the
Yeah, put it
on the
there because
chat.
I don't have access to chat on this machine. It's
Gondolindrim.
Gondolindream. What did I do wrong? Oh, it's an underscore?
.github.io. That's right. That's gondolindrim.github.io slash. So it's missing like the last part.
Ah, okay. Hold on.
Slash Acheron docs. Yep.
Acheron. Oops.
Acheron docs.
Ducks.
Yeah.
Look
so
at
that's basically all where all the documentation is, the files, the
so
change
Quakems
log.
just said he's super glad that you didn't leave the community.
Very glad Gondo hasn't left. Yeah, man, me too. I'm having some a bit of personal issues now, so I'm being really away. But Keeps offered to do this streaming, and I just couldn't be off. And I also have some projects that I need to finish right now. But yeah, I'm just taking some time away. I was very surprised by the community response to the post. I was really expecting some bad blood, like people saying crap on the thread, but no, not a single soul.
It was very wholesome in general.
I was very happy by that. I was genuinely wishing, like, wanting to just leave it alone and do another thing. I have plenty other hobbies, but yeah, the community reaction was awesome. And yeah, Quakems also went looking for me, and we did chat a little bit of Discord. He's an amazing guy too, and that just meant a whole
I don't know
lot
about
to me.
that. You're saying
I'm really
Quakems?
thankful for him.
I don't think so, man. Just
What's
messing.
that?
You said that Quakems is a nice guy. I don't know about that.
He's a really nice guy, man. He's really nice.
I'm messing with him because he's here in chat.
Yes, he is. If you want to, there's a very whole lot there. I have to. There's a lot of documentation that I haven't done still, because documentation is a pain in the butt to do. But the Shark page is almost complete. So if you look at the Shark on your left, there should be like a Shark part.
Yep. Introduction.
There you go.
Contributors, features. Wow, this is very thorough. I can tell you that. How to order the components, the BOM table. And BOM is basically bill of materials for everyone in chat, which is the list of components you will need to get in order to make this work if you're soldering it yourself.
Exactly. You can download the files. So still in Shark, in the Shark part of the site, there should be manufacturing files page. That's Elevate.
Oh, I'm sorry. I'm too stupid. Hold on. Shark.
No, don't spread it, man.
Bill of materials. Which part?
Okay, Shark, the last one, manufacturing files.
Yes. Okay.
And then you have the Gerbers and the schematic. So download the schematic.
It is pointing to a 404.
A 404. Oh, that's awesome. A 404.
Let's see. Hold on. Let me try to figure out why. Shark PCB, and then you were trying to link to master. It's like Gerbers. Oh, your Gerbers now I think are on menu files, and your link
menu files. Yeah, I'll update the link once I can. But yeah, just there is a shark.pdf file somewhere there. I think it's the second last.
There it is.
There it is, and that's the schematic of the Shark. If anyone wants to see everything, and everything is there, and Shark uses STM32F303. So,
so nice.
And it also uses USB-C, right?
Right. The encoder switches, hard reset, power supply and protection, I2C. I2C is the thing that we use for underglow?
Yes, RGB uses I2C, if I remember correctly. Yeah.
Here it is. Here's the
If
USB
you take a
connector.
look at the connector, there you go. So the USB-C connector, it has a little bit more of components, right? It has check the RCC one. The RCC one is kind of wrong. There should be another RCC one there. There should be
Where?
2 RCC resistors, and I'll update that as soon as possible. I haven't had time yet. You also have a shield net there, right?
Let me download
So,
the PDF because I think it will render better. Hold on.
okay, awesome. So Tefram said very well laid out. Yeah, man. You see the PCB has hundreds, literally hundreds of components. So everything is disorganized. Maintenance is really, really hard to do. So it's very well much like coding. If you do spaghetti code, maintenance is impossible. Right.
So here's the shield net for the shield.
Yeah, that's the shield net, and that schematic is a pretty good reference. There are some needs and bits that I should protect, and I will do that once I can. But that's almost a good reference.
It is. It is an awesome.
The USB-C connector has some little bit more of things that you want to do. I will also the COI just followed. That's awesome, man. Thank you.
Yeah, the COI, and also before Fin Alinea also followed, and I forgot to say that, so thank you.
Oh, that's awesome.
Alinea.
That's awesome.
Fin Alinea. All right, going back to our little.
Yeah. So if you guys want to see what a very well laid, protected, and everything should look like, take a look at that schematic file. What we have right now will do for our first time designer. What we are doing today on KiCad should very well suffice. It will work nicely. So don't be afraid of doing this. Very simple. Strictly, everyone starts somewhere, right?
Oh, for sure.
And well, the very old, I'll always be on Discord if anyone needs to ask what I did and how I did it. That's really not a problem.
Okay, so quick question. Do you want to start doing the second part? Should we go all the way to the grid? Not the grid. How do you call it? The switch stuff?
Switch matrix.
The matrix. Should we do the matrix now? Do you want to pause? What's your...
See, I have all the time in the world right now, so...
Okay, let's do it.
Awesome. So what we do here is, let me see if KiCad has a max underline switch now. Let's see the symbols.
Hello, not D10, and the Koi is saying, new to the Mac community scene, but loving it so far. Community seems great. It is really great, man. I am very pleased with the communities. There are a few problems here and there, like the one that Gondo been through, but you know, in general, it's made of really nice people. And yes, Ephraim, we're definitely posting this to YouTube, and I want to post it right after it's finished. So I'm gonna try to release it, this first episode on YouTube right after. So
yeah, I can't find a good symbol.
MX switch. Okay.
Yeah, for the MX.
We can add that whatever. Do you want to do the Acron library? What is the best?
Yeah, Acron has this good footprint. So yeah, let's do it. I mean, it's ready, right? And I'll just I can't find a good one to use right now, like native. So let's use it.
Okay, all right. So what I'm gonna quickly do is I'm gonna clone this on my local machine.
Not G10. Hey, whoa, what's up, man? How are you?
Oh, I already have it. Of course I do. Let me just move this. Let me remove this. And
try pulling it. Maybe if you have it, you haven't pulled the latest.
Yeah, hold on. Let me just. What is that carabiner? I have carabiner closed, and I like to use caps lock as control, so I was messing up. So let me move Acron library to old Acron, and I'll clone it again. This way we get it fresh.
So yes, how are you doing? I'm good.
I'm good as well.
I'm
I'm pretty excited to be looking at those schematics, and understanding what they are. Okay, so here we have it. Walk me through how I add it here.
Okay. Can I ask you something? Like,
Absolutely.
maybe it is possible. I mean, the majority of people that will try to do this, they don't know Git.
Oh yeah, let's show the other way. Okay.
So can I please ask you, like, just download the repo, like?
Yeah. So you can download the zip file.
Yeah, you download the zip file, and then you extract it right on the PCB files, right? Let me see it.
Oh, right inside. Got it. Okay. So since let me show what I'm doing. So I am saving this on a particular place on my workspace. Mine is on a folder called Code Shark 50. Sure. And I have another Shark 50 inside it. But what Gondo is saying is that I should download it here. So instead of downloading it here, I'm going to basically move.
You should have like an Acron library folder right together with those files.
So create a folder? Or just unzip it here?
I think it's zipped under a folder already. Take a look at the zip file before doing it.
Let's see. Oh, I can't.
Has a folder.
I see something. Yes. So it's called, when you download it, it's called Acron Library -master.
Dash master, which is the master branch, right?
Yes.
So what you do is everything is downloaded now. I will take you through the whole library once we use every part of it. But for now, what we do is we add the symbols, right? We need the MX symbol. What you do is you add the Acron. I have to edit myself. The Acron library folder, and then
I'm showing your screen. No.
Yeah, I just have to copy the library folder myself. Library here. Okay, so I'll copy everything.
I have 40 emails.
So now what you do is you go to KiCad.
Okay, let me go to my screen.
And then there should be preferences.
Preferences.
And then manage symbol libraries.
Yes.
Awesome. And then you go to the tab project specific libraries.
Perfect. Then browse.
And then you browse libraries.
And then you're going to go into the folder where the project is. And then inside there, the Acron library master symbols.
Yes. Symbols. And then there will be a .lib file. And you add the .lib file.
There it is.
So now the Acron library symbols will be added to your KiCad project.
Cool.
So when you go lay down a symbol, you can just add a symbol, and there will be an MX switch.
MX switch, here it is.
MX switch, there you go, MX switch. Okay. Awesome.
So you want to move it inside?
Yeah, I like to move all the labels inside it because we will have a lot of them.
Yeah, of course. That makes a lot of sense.
There you go. Awesome. Every switch has to have every switch has to have a diode, right?
Right.
The purpose of the diode is basically doing the anti-ghost.
Mm-hmm.
The way that the symbol is done is that the top pad, the top pin of the symbol will be the row.
Okay.
And the left pad, the left pin is the column.
Okay.
So what we do is we add a diode, which I like to use the D underline small footprint.
Okay. And then the diode is on the column or on the row?
Okay, so the diode, this is a problem because we generally use the diode ranging from the column to the row. So exactly that. The firmwares will have an option. That depends on firmware.
Call to
Firmwares will have an
row,
option.
row to call.
Yes, QMK has call to row and row to call. The default is call to row, which is that one that we are using right now. So
Perfect.
basically everyone does that, right?
Yes.
To illustrate how it should work, basically, I will add here 4 switches. Which should look something like this. Are you seeing my screen right now?
Yes, let me... There. Yes.
Try doing that. You can just copy the whole switch plus diode group. So that makes life really easier for you.
Quick question. Let me show you.
What's that?
So, can you see my screen?
I can.
I'm selecting everything. Oh,
Yeah.
and then I need to press C, right?
Control C.
Control C?
Yeah, you select everything, let go, and then you press Control C.
Hold on. Control C, and then... No, maybe it's another one here.
Control C, and then Control V.
Ah, okay. Yeah, Command C, Command V. Got it. Okay. Then you place it wherever you want. Then Control V again. Like this. There we go. Okay. We're seeing your screen again.
And now we lay the first rows and columns, right? Which should look something like this. So this is my first row. This is my second row. I really have this thing with the metric stuff, so I'm really careful about that. Here you are. So you are connected here. You are connected here.
How do I stop?
You press escape twice.
No, it's not working. Look, let me show you what I mean.
Let's see. No, I'm seeing your screen.
Okay, so I press W and then how do I stop it here? Like I want it to stop.
Click twice.
Oh, click twice. Okay, got it.
You click twice.
Okay, what else do I need to do here?
The columns. You did the rows, now do the columns.
Ah, okay. Hold on. It's kind of hard to get used to the double click thingy.
Yeah, it's the KiCad. Just KiCad things.
Yes.
The more you use it, the more you get used to it.
Okay, I think I have all the columns ready.
Awesome. So just to make things a little bit clearer, we add those labels now.
Yes.
Right?
Uh-huh.
So let's add labels.
Call 1, call 2, and their global label. Let's put one here.
By the way, you can copy labels too.
Oh, okay. Call 1. Oops. Here, let's copy this one over to down here. Then this one is called 2. Let's copy this here. This is row 1. copy this one here. Let me just move this. Can you move wires? Like redraw wires?
You can delete a wire with backspace or delete, and then just
Got it.
redraw. Any chat questions? That's it.
Does click then enter works as well?
Does click then enter works for what? I didn't.
For finishing the wire stuff. Let me see.
Let's see.
No, it doesn't work.
No, it doesn't. Yeah.
I just tried it, and it does not work.
By the way, the designers will generally have a micropad for these things. So if you work with those kind of things, you have a micropad, a necropad.
Oh, should we do a macropad for this? I think we should.
I think we should. Maybe
We're gonna do one. We're gonna do one. That's gonna be on a future episode.
That's a future episode.
All right. Okay, so we have
Awesome.
2 columns and 2 rows. Now we need to hook them to pins.
Now we can have a glimpse of how a keyboard works.
Oh, nice. Let's do it. Let me show you your
how
screen.
does a keyboard work? It works basically like this. So we have 2 columns and 2 rows. How does the microprocessor? The keyboard is basically in its heart a microprocessor, right?
Mm-hmm.
How does the microprocessor know that the switch? So it's a matrix, right? So let's name it switch 1-1, switch 1-2, 2-1, and 2-2, right? How does he know which switch was pressed? So first, he will do this. He will power on. He will put 5 volts to column to row 1. Okay.
Mm-hmm.
That's what he'll do. He will put 5 volts to row 1. Yeah. Then, when you press a switch, the switch pressing is a short circuit, right? So if you press the switch 1-1, which is the top left one, you are going to short circuit cold 1 and row 1. So cold 1 will be 5 volts. So the microprocessor powered on row 1 and cold 1 went 5 volts. He knows that you pressed that particular switch.
Right.
If you press the switch on your bottom left, then column 2 will be 5 volts.
Mm-hmm. Bottom left or bottom right?
Bottom left. Bottom left.
Call 2 will be 5 volts?
Yeah, what the microprocessor does is he powers on row 1. He puts row 1 into 5 volts.
Okay.
And then if you press the first switch, the top one, the top left one,
Mm-hmm.
It will short circuit row 1 and cold 1, because
Right.
that's what the switch is, basically a short circuit, right?
Yes.
And that's how the microprocessor knows which switch you pressed.
Okay.
Because if you press the bottom left one,
Mm-hmm.
it will be cold 2 that will be powered on.
Call 2 or row 2?
Cold 2, because
The bottom left? How does it connect to call 2?
yeah, you see that you basically changed pins, right? The colds and rows on your screen, they are switched.
No, they're not. I fixed the in. So if I
It's because your screen is frozen on me. Yeah, you're right. So it's the other way around. What the microprocessor does is he powers cold 1.
Call 1,
Cold
okay.
1 equals 5 volts. When you press the first switch, which is the top left one,
it's gonna also get 5 volts into row 1.
into row 1.
Yes.
So he does that 1,000 times a second
Mhm.
with 1,000 hertz. He keeps switching on and off the columns.
Right.
So first column 1, then he turns that on, then off, then he turns on cold 2,
Mm-hmm.
and then he turns that off. The caveat here is that you can't press a switch for fast enough, like in a millisecond fast enough so that he doesn't get your key press.
Right.
So for each press that you do, he will have swept, right, the whole keyboard 2 or 3 times.
Yes.
So that's what.
Hey, what's
that's
up? Clavier is here. Sorry.
Matrix.
I just saw that he said hi. Sorry for being slow with the chat, but Clavier is
No,
here.
that's no problem.
Acrylic master. Yes. So I got it. So every time. So what you're saying is that if he puts 5 volts in column 1 and we're pressing row 2, sorry, when we're pressing this switch here, it will have 5 volts on row 2.
Exactly.
Okay.
Why do we have the diodes though? The diodes are important because say that you press the top left key.
Top left. Okay.
So you press that one. If the diode were not there, if you just short-circuited the switch, that switch would have also short-circuited row 1, column 1, and then it would also have, let me see this.
Column 2.
If you press, say, the 2 top switches at the same time, right? Can you agree with me that the whole matrix will be 5 volts?
159 just cheered 1,000 bits. Thank you so much, man.
Oh, that's awesome, man.
Appreciate it.
Bits. Oh my god. Thank you so much, 50.
Sorry, Gondo, go ahead.
No, that's when
so if you press the 2 on the top.
Yeah, say you press more than one switch at the same time. Say you press switch the top left one and the bottom right one, like the 2 diameter ones,
okay.
Right? When you press the top left one, it will short circuit call 1 and row 1.
Yes.
Right? But at the same time, you will have short circuited row 1 and column 2.
Yes.
So the whole matrix will be 5 volts.
Yes.
And the microprocessor will interpret that as all switches were
pressed. All the 4 switches are pressed because if you have column 1, column 2, row 1, and row 2, that means that you have pressed 4 switches.
Exactly. So that's why the diodes are there, because what a diode does is it conducts current one way, but it doesn't another.
Right.
Right. So on the first switch, if row 1 is lit up, it won't automatically short circuit call 1, because the diode prevents that from happening. See what I mean?
No. I'm trying to, but no.
Suppose that I press the top left switch.
Yes,
right?
top left, this one here.
Top left. Better yet, suppose that I press both top switches.
Okay, both top switches, yes.
So in the first instant, the microprocessor will turn column 1 up, will turn it 5 volts. The problem here is that since column 2 is not powered up, it's 0 volts.
Column 2 is not, yes.
Is not powered up yet.
Okay.
So what the diode does is that it blocks the row 1 5 volts, because you will have pressed the first one. So row 1 will be 5 volts too.
Right.
Right. If we didn't have the diode there, column 2 would be short-circuited.
Oh yeah, and I understand now. Let me see if I'm right. What would happen is the following. If this is pressed, what would happen is if you have 5 volts here, it would come this way, all the way to the switch, and then all the way back to row 1. Why? Because it's pressed. But the problem is if you didn't have this diode here, what would happen is this would also come here and back into this switch bulb, but then it would be closed. So I don't get why column 2 would be light up.
See, if you didn't have the diode there, so column 1 is turned on.
Yes.
And since the left switch is pressed, row 1 is also turned on.
Yes.
Okay.
Yes.
But since you don't have the diode, you have a straight short circuit there. Since the second switch, the right switch, is also pressed, it also shorts call 2.
Right. If you don't have the diode, yes.
It shouldn't be. So that makes for spaghetti problems on the microcontroller.
Hold on, Gondo, because I think I am stupid. Hold on. Let me.
What's that?
So row 1 is on, right? It's 5 volts. Then you have both switches pressed, right?
Yes.
So it comes, and then you have 5 volts here on column 1. That I understand because this is pressed, right?
Sure.
Isn't column 2 supposed to be 5 volts because this switch is pressed as well?
That's the problem. It shouldn't. It should be 0 volts. Each column should be 5 volts for a single instant of time. First, column 1 is 5 volts, then it's turned down. Then column 2, then it's turned down. Then column 3, then it's turned down. So the columns, they what's the English word for intercalar? I have no idea. They keep
intercalar is not
I have no idea.
Intertwine, I think, something like that.
Yeah, the columns, they are turned on one by one, right? So first column 1, then column 2, then column 3. There shouldn't be 2 columns 5 volts at the same time. So that's what I'm trying to say.
What you're saying is that if row 1, so switch 1 is pressed and switch 2 is pressed, right? Mm-hmm. What you're saying is that current is gonna come here from row 1. It's gonna follow this path, right?
The microprocessor lights up the columns, column 1.
Yes, okay. But the fact that row 1 is 5 volts, interpurse.
I had no idea.
Me neither. But I think there is a better word. Okay, hold on. Let's see if I can make this understand this. So row 1 is 5 volts, right? So energy is flowing, and down here, since this is closed, it's gonna flow all the way back to column 1, right?
That's the opposite. The microcontroller powers up the column.
Oh, okay. Sorry. So 5 volts here. Oh, I see. So it goes here and then here, right?
Yep.
But if I check the current here, is it 0?
I can't see our cursor on the screen now.
Sorry. I don't understand why if I have... So hold on. Oh, 5 volts here. And then row 1 is going to be on.
Let's do this.
Hold on.
Let me show this. Okay, so can you see my screen?
Now I can.
Okay, let me share you the right screen. Let me switch to Zoom.
I totally understand what the diode does, but I don't understand how energy is not flowing all the way. Oh, I know now. Can I try to explain? I think I understand now, Gondo. Hold on. If it's column, it's like this. What happens is, from column 1, it goes through the switch, through here, and to row 1, right?
Exactly.
But it doesn't go to the right because it stops at the diode. Energy never flows from here to here.
It never flows backwards.
That's why column. Yeah, that's why column 2 doesn't get 5 volts back from this. So you're when you put 5 volts into column 1, only row 1s get 5 volts, but not column 2.
Exactly.
I understand now. Okay. Totally understand now. That's why we have the diode there. Is because when you're, let's call it, actuating this first switch, even though the second one is pressed, you don't, when you're scanning that particular column, you don't want column 2 to be perceived as being on, right? So energy comes from this column into the switch, out here, and then triggers row 1. But what happens here is energy would tend to also flow towards this direction and here and go all the way to column 2, which would indicate that that switch is also pressed, which is wrong because that would be a ghost because you're not scanning that column right now. So what is happening is energy comes from column 1 all the way up and it tries to go here, but then the diode says, you know what? You cannot pass on this direction. So it only goes to row 1. Totally understand it now.
That's
Thank you so much.
What happens.
Understand it.
So that's why the diodes are there. That's why every single switch has
Intercolor
to
is alternate. That's the perfect word.
alternate.
Yes.
Yes, alternate.
Thank you,
Yeah.
super normal like. Yes, that's the word I was looking for.
I had what's called a brain fart.
Yeah, same here. Like, same here.
Yeah, I didn't remember what it was. So that's
Cool.
basically how a keyboard works. The microcontroller alternates the columns, so he sweeps a particular column at a given time.
Yes.
And he sweeps the columns basically in the order of 1,000 hertz. So his column sweeps 1,000 times a second.
Yes. Perfect.
You know. So the minimum latency between keyboard and actuation and computer actuation is a millisecond.
Mm-hmm.
So that's basically how a keyboard works, right?
Yes.
And you can ask me why it's not the other way around? Why doesn't the microcontroller power the rows, scan rows, and
right?
read columns? You can do that too. That's why there is the column to
row and row
to column.
Man, I'm learning so much. I'm not even kidding.
So the firmware difference is basically how the diodes are set. It's basically how the columns are read on the firmware. That's why the column to row and row to column is important.
Yes. Okay, so I think what I can do as a homework is to prepare the whole matrix. Oh, but I think we should talk a little bit about the matrix, right?
Yeah. You know what? Let's do this first. The matrix here is on the schematic. The matrix is basically like this. It's each switch has to have a symbol.
Right.
That's what it happens. First, what you should do is implement a single layout. So the PCB that you're showing right now on KLE, it is a multi-layout.
Right. Oh no, yeah, we should do only one for now.
Yeah. So for now, let's do like the main
yes.
layout. There.
Let me get rid of everything else. So, and I consider the main layout to be this. Hold on, just FYI, I want to have shift and function because otherwise you can't have like HHKB row arrows, and then without that you're basically dead. You could use shift for that, so we could use that. But let's do this one here, right? So here's what I use. I use the QMK builder or something like that to auto draw the matrix for me. I don't know if that's a good idea or not.
Yeah, it is a good idea because it's an easy.
It is an easy
tool. Particularly, I don't like it.
Really?
Yeah, because it hinders your ability to work with the matrix.
Okay. Let's not do that.
Philosophical, right? The thing is, the matrix is not static. You don't set the matrix the way it is, and then you just work. Sometimes you have to go back and forth between PCB and static, adjusting layers.
Yeah, that's true.
And rows. So it is a very interactive process between the two of them, and you should be very aware of that in the design process, right? What we should do now is, let's just suppose that we have one of those very, very tiny micropads that have only 4 keys. And, what we are going to do now is, we are going to assign every component to a physical component. Because as they stand right now in our PCB, every symbol is just that. It's a symbol. It symbolizes something.
Right.
So, for example, in the start of the stream, we had this little problem that, so which package for the microcontroller do we use? We use the QFP or we use the QFN?
Right.
So that's how we tell. Now we will tell KiCad, the program, which packages he should use.
Yes, cool.
Right? So now let's do this. First of all, what we are going to do is, on the top of your screen, there should be a symbol that is a paper and a pencil.
Yes, found it.
So it's called something like Annotate.
Annotate schematic, yes.
Awesome. So you just leave it as it is and you press Annotate. Just plain Annotate.
Right.
Awesome. And if you take a look at the schematic now, all the components are numbered now. Remember that it did that automatically?
Yes.
Everything is numbered now.
That's so cool. Oh, quick question. I have, I don't have a switch. Oh, yeah, I was going to say I don't have a switch 1, but switch 1 is probably the reset switch, right? Yes.
Exactly.
And that kind of sucks because now the diodes have different number than the switches.
Yeah. See, if you take a look at the schematic on Shark, every diode and every switch have the same numbering.
Right.
Unfortunately, since the annotation is done automatically, and I think it's done by order of appearance, you have to set that up by hand. So you have to edit every single diode and every single switch with the number that you want.
Okay. Yeah. That's fine.
That's not good. I mean, you take some time, like a very long time and a very tedious task to do, but it really helps maintaining your PCB in the sense that, when you have a PCB layout, when you see that B2, you know that's the diode that goes to switch 2. So you have a very clear distinction between every component and their designator. It really helps to do that kind of thing. Take that time to organize your schematic in a very, very, how can I say this, polite way, having it very strictly organized.
How do you think is the best to have like diode and switch 1? Like 1, 2, 3, 4, right? Would be best.
So what you could do is rename the push button to SWP or to push 1.
Yeah, I did 99, but SWP is now
SWP1.
Right.
And then you can put switch to SW1.
Yes, that's what I'm doing. But I was asking if you like to go by row or by column. I think by row is better, right?
Yeah, I like it by row, but that's completely personal preference.
Okay. Okay, mine is organized now. So we have switch 1, diode 1, switch 2, diode 2, switch 3, diode 3, switch 4, diode 4.
Awesome. So save, don't forget to keep saving.
I just did.
So everything is numbered, everything's clean. So now what we do is we will assign footprints.
Okay.
Right. First, what we're going to do is still on the top, on your top menu, there is this symbol there. That's right on the right. To me, it's on the right of a ladybug. So
yes,
there's a ladybug
I have
symbol.
it. I have it open.
That's it. And to me, it's called assign PCB footprints to
schematic symbols.
So it's going to pop up on your a window is going to pop up for you.
It didn't. It says exporting the netlist requires a completely annotated schematic. And it opened the annotate schematics once again.
Okay, I think you pressed the wrong one. It's the one right next to the ladybug.
Yeah, it's called assign PCB footprint to schematic symbols.
Exactly. Try that. Let's see what happens.
I did, and it opens the annotate schematic. I don't know why.
Try again. Annotate.
Okay. Done. Let me... Oh, and then it opened, and then it crashed. Hold on. Let me reopen.
That never happens. How did it happen? I have no idea how
to
to
reopen the schematic.
Okay, so Super Normalax says, I don't speak Portuguese, but thankfully it's close enough to Spanish that I knew exactly what you meant. Oh, hola, ¿cómo está?
¿Cómo está tú?
¿Cómo está tú? ¿Cómo está usted? Usted. It's not tú, it's usted, man.
Tú existe. Los argentinos hablan mucho tú.
Yeah, but los argentinos usan un español.
Boludo, sí, claro.
No bueno español en Argentina. En Argentina no nos hablan español, les hablan porteño.
Mira, esquema se salió. I don't know how to say unexpectedly in Spanish. Oh my God, look at this. Oh.
My GF, she studies in Argentina, right? She studied medicine in med school.
And sometimes we are talking and she starts speaking Spanish, and I just keep hearing like, what the fuck is she saying?
I like how Argentinian they say like boss, like you,
Boss, yeah,
usted, they
boss.
say boss. All right, I have it open.
Okay, so let's see. Awesome. So what we do now is, this may seem a little intimidating, like there are a bunch of numbers and letters and things, but let's get through this. First of all, we need to set if we want to use SMD or THT components. Let us assume that
for
we
this
will use SMD components, right? What we will do basically is assign every component a physical size, a physical component.
Right. It's basically getting the idea of a switch and saying, for this switch, we're going to use this particular switch, this model of switch that's going to look like this, right?
Yeah.
It's like putting a physical sense to something that we only have the idea of so far.
Exactly. What is problematic here is that the same component can have many packages. It can have many sizes. It can have many models. So a 100 nano capacitor can be 0402, which is a 1 by 2 millimeter package. It can be 0603, 0805, and there are hundreds of packages that you can use. For the capacitors, we will use the 0805 package.
Right. And then you have two options, right? So basically here you have a list of all the components that would be able to be applied to C1, right? For this 22 picofarad capacitors, and your job is to go here on the right and find the right one. So you're going to see that like for capacitor there is a dozen, and what Gondo is saying is that we're going to use the 0805, which is 8 millimeters by 5 millimeters. Is that what it is?
The 0805, no, I think the 0805 is 5 by 3 millimeters or something like that.
Oh, okay. So it just does. Different numbers are the different sizes, right?
Are the different sizes, basically. I think 0805 is in imperial units, if I'm not.
Okay.
Or something like that, yeah.
And then we're gonna see that we have two different footprints for the same capacitor. One is 0805, and the other one is 0805 hand soldering, right?
Yeah.
Can you explain?
The 0805 has, if you take a look, you can click a footprint. Just click a footprint, and on your top left, there should be this little magnifying glass icon. And if you click that, it will show the footprint that you're seeing.
Okay, so this one, right. I think the pads are a little larger, right?
Yeah, so for the normal, let's say 0805, the pads are a little thinner because that footprint is for you use when you will do everything with the hot air. If you need to use hand soldering, which is very difficult to do, mind you, you use the hand solder version, which has larger pads and it's easy to hand solder.
Okay.
So particularly, I always try to use the hand solder version.
Me as well. A few times.
There are some times that I need to use the normal one because the space is the thing or something.
Yeah.
Oh yeah.
Okay, so for this, I think we can use the hand soldering, right? Okay.
Use the hand soldering one.
So what you do is you click twice for each of the components, and since all of those are capacitors, we're gonna do that for all the capacitors that we have here,
every single one. Yeah.
Cool.
Okay. For the diodes, the most used package for diodes is one called SOD123, which is a package for the most commonly used diode, signal diode, which is the 1N4148, right? Which is the diode we will use.
So let me see.
If you take a look in the library, there should be a library called diode _ SMD. And in that one, there should be D _ SOD-123.
So let's see. The SOD-123.
Yeah,
I found it. Yes. Diodes SMD D _ SOD-123.
Yeah.
That one?
That one.
Okay. Done.
Done. Awesome. Now let's jump for leave the connector alone for a while,
Okay.
and let's jump for the resistors.
Okay.
For the
By the way,
resistors,
if you type R, if you have the diodes here highlighted and you press R, it's going to go all the way to the first R. So that's a shortcut I use. Okay, so we are on the resistors.
Awesome. I didn't know that. That's awesome. Okay, for the resistors, there's the same thing. There are many packages.
Mm-hmm.
I generally use the 1206 package.
1206 hand soldering, right?
Yeah, on the footprint libraries, which is the list on your left, there should be a resistor underline SMD, right? Or something like that. Resistor underline SMD. And inside that resistor underline SMD, there should be a 1206 in head solder version.
Oops. Resistor SMD 1206 hand soldering. Yes. So we're gonna add this one. Done.
Done?
Yes.
Okay. Now, for the switches, for the push button, everything, we will need the Acron library.
Okay.
Right. I think the crystal. I think we have crystal. Let's see. There should be a crystal. Yeah. So there is a crystal library, stock library in KiCad. Right. I think it's the one right up the diodes one.
Crystal. Which one is it? Crystals. Okay.
Crystals. Yeah. And let's use a. I think it's a 2012 one. Let's see. Is there a 5032? Yeah. So let's use the 5032, right?
I still didn't find it. Hold on. I'm still in connectors. I'm going down. Hold on. Crystals. Okay, which one? Crystals SMD?
Crystals. And then there should be a 5032. 5032. 1.
5032, yes.
Yes. So we
pin?
want to use the 5032. Remember that the crystal that we use has 2 pins.
2 pins, I remember.
And remember using the hand soldering version.
Okay, perfect. Done.
Awesome. So, before doing anything, let's save. So you hit that apply save schematic and continue button.
Okay, done.
Awesome. So it just saved. So now what we will do is add the Acron library.
Okay.
So you go up there on preferences and manage footprint libraries.
Done. Then go to project specific and browse.
Exactly. So project specifically browse, and under the Acron library folder, that should be a footprints folder.
Yes.
And that particular one has lots of .3D
Yes.
folders. You can just click one and then click shift
click.
to add every single one, and just add them all.
Done.
And you click OK. So now on your left list,
Acron, I have it here.
so you have Acron Shock, which currently has only one footprint. You have Acron components. You have the components are basically resistors, packages, and other things, connectors. What we will do now is we will do the switches.
Okay. So
Right.
MX or MXA, what's the
So-
difference?
MX is MX only.
Oh, MXA is ALPS and MX.
Yes, MXA is MX and ALPS is the double compare.
Oh, and Evo said way before that 0805 is 0.08 inches by 0.05 inches.
Yeah, it's the imperial units.
Imperial, yes. All right. So, are we doing?
1206 is 12 mil by 6 mil tau or tau,
Okay.
right? And 0805 is 80 tau by 50 tau. So that's how it happens.
Got it.
Thank you, by the way. Evil always helping us. The last stream he did really help immensely on fixing the Tinha PCB, the plate PCB.
Nice.
So first of all, we go to switches, and in Ekron MX, you're going to see a bunch
Yes.
of switches, right? So how it works is this: MX 100 is your normal 1U. So if you magnify that, you will see that it has a 1U.
Yeah, I see it.
There you go. That's your 1U. The age version stands for hot swap.
Ah, how cool is that?
So you can show them the age version.
Nice.
There you go. So there's your hot swap version.
Mm-hmm.
So you have that for 1.25, 1.25H, 150, 150H. When you go to 200, you have 200 and 200R. What's that? So 200 has 200 and above have the stubs, right? So 200 is the stab with the big hole facing down, with the wire facing down.
Got it.
And 200R stands for reversed, which is with the wire up.
Nice. So basically south or north facing?
No, south and north facing are the switch.
No, but the stabs as well.
The stabs as well, awesome. So south and north facing. And then for the R version, there also is the age, right? So you have...
Yes, H and
you have the
HR.
normal one, you have the R one, and you have the HR one.
Yeah, the HR is the one you use when you're fired.
Exactly.
Anyways, bad joke.
The 200 also has a V version,
Oh,
which stands
wow.
for vertical, which
Yes.
which is when you're using for numpad.
Yep. And VR as well.
And the VR, which is the vertical one, but reversed.
Okay. And you don't have the VH and VHR. The hot swap.
VHR. The VHR is not anymore used, man. It's been like 12 years, 15 years or something. VHR. But yeah, I have to do VH and VHR.
Yeah, who
the
cares?
problem is that hot swap is really down these days.
Yes.
And people don't need hot swap numpads. So I'll add them, but they will be forgotten for the rest of their life.
Yeah, for sure. Okay,
but
so
anyway, so that's the coding for every single one of them, right?
Cool.
On the bottom, you have the ISO.
Mm-hmm. I saw. I just opened it.
And you have the vertical ISO too. I have to do the hot swap ISO.
Cool.
So this is when we select which switch is which. For now, let's do our 4 switches as a normal 100.
1U. Done. So I went ahead and did one. How do you clear if you assign it wrong? Just assign something else, or can you clear it?
Yeah, you reassigned it. I think you can clear it. I think you right-click and cut footprint association. Yeah.
I don't have it here.
No?
No.
Yeah, for me, you can right-click and cut footprint association. That's bad.
Interesting. We don't have that on Mac. There must be a way, but I don't know it.
Never used Mac. I really don't know.
Okay, for the switch push, do you have the footprint already?
Yeah. Let me just fix. I screwed up the first call footprint. So it's 5032. Yeah. So for the push button, where's the push? Okay. For the push button in the Acheron hardware, I think. Yeah. On the Acheron hardware library, you'll have the footprint for that hexagonal SMD, very pretty push button.
I don't know why it's not. What's the name of it?
It's SMD push BTM on the Acron hardware library.
I have it on the left side. I don't know if you're seeing my screen. I have it on the left side, but when I click it, it doesn't show anything on the right side. Oh, hold on. Maybe it does. Oh, now it did. Okay, it's the SMD push button. Got it.
Exactly.
Yes, perfect.
And now for the connector, right? We are going to use a very, very common USB connector, which is one that is fully THT, which is really hard to do, really hard to fix, solder, unsolder, and everything. So in the Acron connectors, you will see, and let's use the USB Mini D XM7G.
Got it.
Okay.
Perfect.
So at least for me, and I think as I'm seeing for you too, every single symbol has an associated footprint.
Yes.
So now we click apply, save, and continue.
Yes.
And then just OK.
Done. Okay.
Done? Awesome. Okay, so now we can close our schematic. Just for now.
Closed.
Now we open the PCB file, which is the .kicad_PCB. Right? Awesome. So to import all the footprints, you click on the icon right on the left of the ladybug.
Okay, read net list.
No,
No?
to me, you don't have it. Why the heck don't you have it? Okay, so there is a button that updates right from the PCB. Let's just wait.
What does it say?
It says update PCB from schematic. Okay, so you click tools on the tools menu.
Update footprints.
Update PCB from schematic. No.
Oh, it was minimized.
Yeah, awesome. And then you just click update PCB.
There is an error. Is that okay? I didn't have the package for the microcontroller footprint.
That's a standard package from. Well, let's use the Acron one. Why? Because we have it.
Let's do it. Go back to the schematic.
Go back to schematic, and then you go to that annotation one. So assign PCB footprints to symbol.
Yes, it's fetching the libraries. Hold on. Takes a little while. I don't know why it takes so long on mine.
Because it has to keep reading every single library. So now you go to U1, right? I think it is U1.
U1, yes.
U1, awesome.
Acron.
So you go to the Acron components library, and then there should be a TQFP, I guess.
Yes.
Yeah, for me, it's the last one, TQFP. And you assign that one, and then you apply and continue, and then you hit OK.
Just make sure that I have the right one. I have QFN 44 1EP. Is that one?
No, it's the last one. It's TQFB 44 10 by 10.
Ah, okay. Sorry. Found it. Okay. Apply, save schematic, continue. Okay. Let's go to the PCB. Tools. Update PCB from schematic. And now we have no errors. Then click update PCB.
Update PCB.
And close.
And then close. And then the components should...
yes.
Awesome. And you place them somewhere.
I did.
So there you go. Just for a little... Why do I have 5 switches? Oh, it's the push button. I assigned the push button.
The wrong piece, the wrong
footprint.
That's fine. Okay, I want to propose that we stop here, Gondo, if you can.
Oh, already want to propose? Well, sure, awesome.
And then I'll talk to you off camera, and then we'll figure out when we can do the next episode, and I will let people know. So I think this is a good time to break, because now we're going to be talking about PCB and Rat's Nest and all that stuff that is very complicated.
Exactly.
So I'm going to be pushing everything that we did so far to GitHub, and then every episode is going to be a different branch, so everybody can follow up from where they are. What do you think?
Yeah. Okay.
All right, Gondo, thank you.
Just to show people a nice view.
Oh yeah.
Show them the 3D viewer. For me, it's Alt +3.
Alt +3.
Yeah, I don't know how that is on Mac. It takes a little time sometimes.
Same thing. I have it on my. Yes.
Yeah, so everything should be there, from the connector to the.
This is so nice, man.
To everything.
Yeah, I love it. This is very, very cool to see this thing in 3D.
It is, right?
It is. No, so cool. Yeah, I see the PC, the USB and everything. All right, so I'm gonna put this on YouTube right after, and I'll also push everything that we have to GitHub so people can follow the lessons. And as I was saying, you're gonna know that I will do a branch for each of the episodes.
Yeah, do a AP1 branch, AP2.
Yes, correct.
Awesome.
All right. Hey, Gondo, first of all, thank you for your patience, for your time.
No problem.
And thanks everybody who joined and stick to the end. I know it's been very long, but you know, it's what it takes for us to learn. So I knew a lot about the PCB side, but I didn't know anything about the schematics. So I'm really glad we had this lesson. I learned a bunch. So yeah, thank you very much, man.
There we are, man. No problem.
Have a good night, and everybody watching. I was so lost. Make sure you go back and watch it again, Chief N.
I was so lost the whole time.
All right, guys, you have a good night, and Gondo will talk to you for our next episode.
Yeah, guys. Awesome.
Bye, everybody.